Laureate Argento, where also I'm co-author, and she will speak about the use of the concept of R-Funicularity in shell shapes optimization.
Good afternoon to everyone. The work I'm going to show you is about the exploration of the use of R-Funicularity in shell shape optimization. Funicular structure is a structure that is able to carry external loads through axial forces only. When the shape of the structure is not funicular, it is possible to appreciate an eccentricity between the thrust line due to the external load considered and the axis of the structure. So this eccentricity causes the bending moments inside of the structure, and this is the reason why it can be used as a measure of funicularity. It is possible to extend this concept of eccentricity in the 2D structures, so in shell structures, and in this case, generalized eccentricity has been defined by some of the authors, and this is a measure that allows us to know the eccentricity in each point of the analyzed surface and in all the possible directions. Some of the authors used this definition to define a relaxed form of funicularity, that is relaxed funicularity, and this assessed that a shell can be considered R-funicular if the generalized eccentricity belongs to an admissible range that can be decided and defined by the designer. And so in this case, the structure can be considered R-funicular. And through some mathematical machinery, it is possible to evaluate the maximum and the minimum eccentricity in each point of the surface. So what we tried to do in this work is to develop an optimization process based on the minimization of this generalized eccentricity. So these are the main steps that we of the optimization process. So first of all, it is necessary to define a starting shape. Then an objective function is defined depending on the generalized eccentricity. So the optimization process can start, and the shape is variated in order to minimize the objective function. And then it is possible to define an admissible range for the generalized eccentricity and to check if the minimum and the maximum values of the eccentricity belongs to the defined range. The shape function that we have analyzed has been obtained by a linear combination of 3 shape functions that are taken from the approximate solution of the membrane theory. Specifically, we used the first 3 even functions of the approximate solution that you can see in the top left formula. So this is the shape optimization algorithm. I will go deep into the details. I just want to highlight two important things. So one is that the updating of the shape is made by variating the coefficients C1 and C2 of the linear combination that I showed you before. And the second thing is the objective function that we have used, because as in all the inverse problems, it is possible to define more than one objective function. And in this case, we used the objective function 1 whose goal is to minimize the difference between the actual eccentricity and the admissible eccentricity defined. And the second one has the goal to set to 0 the minimum and the maximum eccentricity. These are one of the results that we have obtained. The structure that you can see is obtained by a finite element model. And you can see in the left, in the top left picture, the distribution of the generalized eccentricity before the optimization process, and in the right side after the optimization process. And the optimization has been performed considering the structure subjected to self-weight load, and a thickness of 10 centimeters has been considered. So it can be observed an improvement of the generalized eccentricity, and that is obtained by a very small variation of the shape that you can see in the bottom picture. So this was a preliminary study that we have performed to understand if it would be a good idea to use R-Funicularity in shape optimization, and we will do other analysis using different boundary conditions and different applied loads. Thank you for your kind attention.
Thank you, Gloria, for being time. And there's a question from Francesco Tornabene and Sigrid Adriansen.
Yeah.
Francesco, please, first.
Thank you very much for your nice presentation. I have only a curiosity, really. In particular, you use membrane shell theory to obtain in your model?
No, it has been used. The approximate solution of the membrane theory has been used just to extract the shape functions. Okay. So we have taken the first 3 even shape functions of the approximate solution. I can share again. So these 3 that you can see. So we used these 3 and we have combined them to obtain a resulting shape that have been optimized, and by variating the coefficients C1 and C2 that are the coefficients of the linear combination.
Okay, thank you very much.
You're welcome.
Sigrid, please, yeah. Gloria, take the presentation shared.
Yeah, Gloria, great presentation, also really interesting work. I have a question. Your original shape, the parabolic veloidal shell, so that is not, by itself, it is not like, it does not exhibit just membrane behavior, and if it doesn't, why doesn't it do that?
It doesn't show a perfectly membrane behavior. So this is the eccentricity distribution that you can of the initial shape, and so the model that we used is a thin shell model, and so the structure is as a thickness, so is characterized by a bending stiffness. So the self-weight load causes the generation of bending moments. So especially in the edges. And also, depending on the boundary conditions, the behavior is not perfectly membrane.
Mm-hmm. Yeah, so what you say is basically due to the thickness, right? That you get bending occurring.
Thickness and boundary conditions too.
Yeah. All right. Okay, wonderful. Great work.
Thank you.
Again, thank you, Gloria.